Let me define a Banach space. A Banach space is simply a normed vector space which is complete. Let me give you an example. Rn. Rn is a Banach space because it is a normed vector space which is complete. Now let's look at this space here, C01, the space of all functions that are continuous with the usual topology for R from 0,1 to R. Now I can define a norm of f being defined as the integral between 0 and 1 of the absolute value of f in between 0 and 1. So this norm and this space, the question is this a Banach space? The title kind of spills the beans. The answer is no, it's not going to be a Banach space. And the reason why it's not going to be a Banach space is because it's not going to be complete. Look at this function fn. Fn is 0 from 0 to 1/2 minus 1 over n. And then from 1/2 plus 1 over n to all the way to 1, then it's going to be 1. And in between, what we have is just a straight line. So you can actually find the equation, the formulation of f of x, which will define such a function. Obviously, there will be three pieces, and you can find the equation for f of n, for f index n. What I'm saying is that f index n is going to be a Cauchy sequence. It's, however, not going to converge in the Banach. It's not going to converge in C01, and here is the reason why. If you look at f of x defined as 0 from 0 to 1/2 and then 1 from 1/2 to 1, then the norm of the difference is going to be 1 over n. You can compute the integral or simply look at it graphically. I mean, if you do it graphically, it's 1 over 2n plus 1 over 2n. And then what you have here is a function f, which is not in C of 0, 1. So fn is a Cauchy sequence of elements of C01, but the limit is not in C01. So what we have is lack of completeness. Therefore, C01 is not complete. Subsequently, C01 is not a Banach space. Now, the question is LP a Banach space? The Fisher-Ries theorem states so. For any p, 1 or plus infinity, any number between 1 and plus infinity included, LP is a Banach space. We're going to prove it. I'm going to start the proof for p equals infinity. In other words, I'm going to prove that L infinity is a Banach space. Well, we already know that it is a normed vector space, so what I need to prove is completeness. What I need to prove is that if fn is a Cauchy sequence in L infinity, its limit is indeed in L infinity. So let's do that. I'm starting with fn Cauchy sequence in L infinity. Well, since it's in L infinity, what it means is that for any k, any integer k, there exists an integer capital N such that n greater than m greater than n implies fn minus fm smaller than 1 over k. And that is obvious because the definition of a Cauchy sequence is that for any epsilon, there exists an integer capital N such that fn minus fm, the norm of fn minus fm, is smaller than epsilon. So if it's true for any epsilon, I can choose any k in n star, and that must be true. Now, there exists a null set ek such that fn of x minus fm of x is smaller than 1 over k everywhere but maybe on this null set. And this is the definition of the norm of L infinity. So this here, fn of x minus fm of x smaller than 1 over k, is guaranteed for any k, provided I choose a capital N which is large enough. But we can also define E as the set of the union of all of these EKs. And E is a null set as a union of null set. And just as a reminder, a null set is a set which measure is 0. Now, let me choose x in omega, but not in E, not in this union of null sets. So I choose x in omega minus E, and I will consider the numeric sequence fn of x. And it is a numeric sequence because I compute fn at x. So for each n, there is a number fn of x. So it's a sequence in the sense of calculus, numeric sequence. It is a Cauchy sequence. But it's also a Cauchy sequence in R because it's a numeric sequence. Now, we note f of x its limit. And what we have is that fn of x minus fm of x, this numeric sequence, is smaller than 1 over k for x in omega minus E. Now, if I take m to the limit, what happens is that fn minus f of x, or f of x minus fn of x, is the same, will be smaller than 1 over k for any x in omega minus E. So if you look at it, it means that fn minus f of f minus fn, the norm in L infinity, will be smaller than 1 over k, and f belongs to L infinity of omega. Indeed, fk is in L infinity, f minus fk is in L infinity, and L infinity is a linear space. So what we have is that f minus fn, its norm in L infinity, goes to 0. So what we have is that fn converges to f in L infinity, and f happens to be in L infinity. So what we have is the fact the Cauchy sequence converges in L infinity. Now, what happens when we have p between 1 and plus infinity not included? So p is a number, and we look at LP. And again, we start with a Cauchy sequence in LP, and we're going to show that this Cauchy sequence converges in LP. There will be several steps. The first one is to prove that there is a subsequence fnk, so I'm going to extract a sequence of fn, and fnk such that the norm in LP of fnk plus 1 minus fnk is smaller than 1 over 2 raised to power k. And we'll see the reason why I'm doing this 1 over 2 raised to power k. It's also true with another number here, but I choose 1 over 2 raised to power k for a reason. We'll see this in a minute. So I'll prove this. That's step 1. To prove this, well, we know that fn is a Cauchy sequence. So we know there exists an n1 such that after this rank n1, fn minus fm in LP, in the norm LP, will be smaller than 1/2. And I will choose small n1 equals capital N1. And there exists an n2 such that after this rank n2, fn minus fm in norm LP is smaller than 1 over 4, 1 over 2 raised to power 2. And I will choose n2 as the maximum of the n1 I just computed, and this n2, this rank, guaranteed by the fact that fn is a Cauchy sequence. And I keep going this way, and I will build fnk by induction, and I will have fnk plus 1 minus fnk in norm LP smaller than 1 over 2 raised to power k. Now, I will prove that fnk converges in LP. And to do this, I will start with a function gm of x, which will be the sum from k goes from 1 to m of n k plus 1 of x minus fnk of x. And if I do this, then I can just do the math and show that gm in norm LP is smaller than 1. And to do this, I just write all of my fnk plus 1 minus fnk. And since I know that each one of the fnk plus 1 minus fnk is smaller than 1 over 2 raised to power k, I can just use the fact that I know how to sum this 1 over 2 raised to power k. And it is a geometric sequence. It's a geometric series. And then what I can do is compute the sum. And I know the sum is going to be smaller than 1 minus 1 over 2 raised to power m, m being the index of G. And this is going to be smaller than 1. So by the way, this is the reason why earlier I showed that f n k plus 1 minus f n k had to be smaller than 1 over 2 raised to power k. So my GM in norm LP is smaller than 1. And there is a theorem called Bepo-Levy, and you can look it up as a link here on this website. And Bepo-Levy provides that the function g that is defined as the limit of the GM will be in LP. And it also says that GM minus G in norm LP goes to 0. Indeed, GM is an increasing sequence, and it is bounded. So for L and K with L greater than K, we have FNL minus FNK computed at X, which will be smaller than all of these sums, which will be smaller than G of X minus GK minus 1 of X. And that will provide me with the fact that FNK of X is a Cauchy sequence in R. But a Cauchy sequence in R converges in R because R is complete. So I will choose to note fx, its limit. And what I will have by taking L to the limit is that f of x minus f and k of x is smaller than g of x minus gk minus 1 of x, which happens to be smaller than g of x. So if we recap this, we have f of x minus f and k of x raised to power p that goes to 0 almost everywhere. And we have f of x minus f and k of x raised to power p, which is bounded above by g of x raised to power p. And there is another theorem called the dominated convergence theorem, which will allow us to prove that f is in LP and f minus f and k in the norm LP goes to 0. Now, there is a step 3, which is to prove that Fn converges toward f in LP. So far, we know that f is in LP, but we haven't proven yet that Fn converges toward f in LP. And what we need to prove is that the norm of Fn minus f in LP goes to 0. So I start with an epsilon, any positive epsilon which is not 0, any non-negative epsilon. And I'd start with n in n being an integer. Now, there will be an m that will be larger than n, and that will be such that it is a nk for a given k. So remember, we have an f and k, and what I choose is an index m, which is a nk, but which is also larger than n. I know that Fn is a Cauchy sequence. That was what I started with, because again, I want to prove that if I have a Cauchy sequence, it converges. So I know Fn is a Cauchy sequence. So I know that for any epsilon prime, then there is a rank after which my Fn minus Fm will be smaller than this epsilon prime. And I'm saying epsilon prime because I choose to set epsilon prime to epsilon over 2. So what I'm saying is that there is a rank after which Fn minus Fm in norm LP is smaller than epsilon over 2. But I also know that f and k converges toward f. So Fm minus f in norm LP will be also smaller than epsilon over 2. And the reason is that Fm is somehow a f and k. So I know that Fn minus f in norm LP will be smaller than Fn minus Fm in norm LP, which I know is smaller than epsilon over 2, plus Fm minus f in norm LP, which is also smaller than epsilon over 2. So the bottom line is that Fn minus f in norm LP is smaller than epsilon, which means that Fn converges toward f in LP.